One last fun example that we get to look at here. This is a very interesting one because we know we're going to have not a horizontal asymptote but a slant asymptote because the degree of the numerator is bigger than the degree of the denominator. So we won't have a horizontal asymptote, but we're actually going to have not even a slant asymptote. You'll see how in a moment. We're going to factor first. We can factor the denominator. There's no way to factor the numerator. So when we do that, our domain from negative infinity to 0, from 0 to 1, and from 1 to infinity. The denominators end up not canceling out at all, so we have two vertical asymptotes, 0 and 1 to begin with, so already we have a bit of an interesting scenario going on, and no holes in this problem. X-intercept when we plug in, or y-intercept is when we plug in 0, so that's actually going to be cool right off the bat, something we haven't seen yet. We get 0 on the denominator. We can't have that, so we're not going to have a y-intercept. When we set equal to 0 in that numerator, there's no way to factor that. That's actually a very interesting problem to try to solve. That's above our algebraic techniques. We're actually going to tell you right now there are no x-intercepts either. So we don't have a lot to go on right now. We're going to have to go just based off of our asymptotes here. We have a couple vertical, and we know we're going to have a slant asymptote. When I do this long division, look what's going to happen. I'm going to get not an x, but an x squared. Yes, it's actually possible to end up with a slant asymptote that's not a slant. This is actually literally a quadratic asymptote. So have fun with that. So the last thing we have to find out, though, first is when we cross this quadratic asymptote, well, if we set the remainder equal to 0, 4 doesn't equal 0, so we don't cross it either. So here's what we have. We have vertical asymptotes really close to each other at x equals 0 and x equals 1. We have a quadratic asymptote. So it literally will go based off of how we know the quadratic goes. So at 2, we're at 4, and at 3, we're at 9. Same going in this direction. By 2, we should be at 4, and by 3, we should be at 9. Our graph, in theory, should follow all of those dashes. How in the world is that going to happen? Well, since we don't have any points to deal with, the only way that I know I can follow these lines and try to basically try to not cross the asymptote because we're not allowed is, well, if I go something maybe like this for that part, and then it's going to continue on forever, something like this for that far right part, and the only thing we don't know is in the middle whether we're above or below the axis. Because we're real close, we can't necessarily say that we're going to go up in between or go downwards, but if you plug in like negative 1/2 into this equation, you're going to end up getting a negative value, so you're going to end up drawing something that is way below. Even 0.5 is actually going to be way down low like this, even lower than that, like at negative 15. So not a huge deal, but we at least know that it's down in that direction. So what I want you to do, though, is if you look at this graph, which we're going to use on our calculator, and what I'm going to do is I'm going to draw in a bit of a thicker line what our slant asymptote is supposed to look like. So first, let me just draw out what the original graph is. There it is, right there, that vertical line representing your, your vertical asymptote going on there. If we take what we think is the horizontal or the slant asymptote, the quadratic asymptote of x squared, and graph it, look how right spot on it goes with what our graph looks like. Even if I zoom out a little bit, let's zoom out. There's your graph, and there's your horizontal asymptote. It matches almost perfectly. So that's why these asymptotes and this end behavior really ends up being a big part of what we do in advanced mathematics.